Hi, I'm Ken Miller.
And I'm David Erdos.
And welcome to the Erdos Miller New Technology Podcast, where we spend our non-productive time talking about everything drilling tech. Our guest today is Michael Ashcraft, who's a mud engineer with Geo-Drilling Fluids. Welcome, Michael.
Thank you. Happy to have you.
So, David, we've talked endlessly about, NWD and mud pulse telemetry and EM on this show, right? But we've never actually spent a second talking about the actual mud.
I have to admit, I know virtually zero about mud, other than there's two types that I know of, and it's used to weigh down.
Types, so I think we're already in trouble.
Yeah, we're already in trouble.
There's a lot more than two types.
Yeah.
Well, it's like water and oil based. That's all I know.
Right. Yeah.
So, I think today we'll just start from the basics, right? Like, why do we need mud in the drilling operation at all? What is so important about mud, right?
Yeah. Probably the most important thing you've got with mud is hydrostatic, right?
Right.
That's what keeps your wellbore stability with pressure, under pressure or over pressure. There's, mud drilling fluid in the wellbore is keeping it off of you, right? That's probably your number one.
I remember going to wild well control in college, and that was really cool. We got to do the whole well control class, and they just basically explained that, like, the analogy of, like, it's like when you're digging a hole in the ground as a kid, especially here in Texas where the water table is so shallow, right? You dig 3 or 4 feet down, water starts coming in, it starts collapsing, right? You got to have the hydrostatic pressure to balance that out. Is that the proper, 5-year-old analogy?
That's exactly right. Yeah, that would be number one. Number two would obviously be you got to carry those cuttings out. And, and then from there, you've got lubricity, you've got filter cake that'll keep a wellbore from, getting swollen and start falling in on you. That, that gets down to different chemical properties that, if you've got a reactive shale versus a salt formation versus, gumbo mud, like East Texas or Louisiana. And so yeah, mud can provide, chemicals that affect the way that soil or shale reacts in a positive way for your drilling operation. And then it also keeps your assembly cooler, provides an ability to keep it cooler. So, you get, as you guys well know from the tool side, gets pretty dang hot.
Yep.
And, if you didn't have a way to pump, a drilling fluid down there, that creates a cooling ability that's also pretty important.
David, I think the tools we've ever seen come back that are like the most destroyed and charred and discolored from heat are always the tools that, like, they lost circulation, they got stuck in the well, and it just sat there statically for days and let it come up to, like, the full temperature of the formation, right? And like that was always the most damaging stuff we actually saw coming back.
Oh, I bet.
Yeah, and so you guys have to like very carefully, perform this art of engineering a fluid, which is a mixture of some sort with like a base and additives and whatever else. And you have to try and tackle all these problems at once, right? You have to understand what the hydrostatic's got to be. You got to weight it up correctly. You got to design it for, like, how you want it to react with the formation, what kind of formation you're dealing with. I mean, there's a lot of things or considerations that go into, like, how you actually engineer that mud on, like, a well by well basis.
Absolutely. That, nowadays with the technology and so many offsets, typically you've got a lot of the answers to the questions a lot of the questions already have answers. And so you've got offset wells that you can either, get hold of a drilling company and operator and, buy that information off of them, or you've got somebody who works within your organization who's been in that, basin and can tell you, okay, this formation, Wolfcamp A, Wolfcamp B, Delaware Basin, Barnett Shale, Haynesville Shale, and they've got, a decent idea of where at least you're going to have a baseline to start with, what kind of fluid you want to run. But yeah, there's a lot of questions that have to be answered from the mud side. Big operators, really, they already know the answers, and all you're doing from the mud side is you work together with their technical support in the office and come up with a mud program that they're happy with. They want to still be leading the charge for the most part, because at the end of the day, they've got the biggest risk. And so, you put together a mud program with them, kind of almost in concert, and then they go through and go, we don't like this idea, or we think we'll run a 10 water loss as opposed to a 20, because we'd rather spend a little extra money on, pack, or a little bit of extra money on starch and not risk losing our wellbore or something like that. But yeah, there's a lot of things that go into a drilling fluid, just, very similar to an MWD or how guys are going to, it's you say mud engineer, it seems like, oh, we're going to throw some water together with a little bit of dirt and send it down hole. It's quite a bit more complicated than that, but it's also not as complicated. If you're inside this world, it's not as complicated as it seems when you're looking into it, from the outside. When I look at you guys work with your tools, I mean, it's like, it's another language.
Yeah,
might as well David, be another language. And, that's the same way for guys looking at a mud engineer.
Dave, we just, NWD, just take some metal, you make it into barrels, you slap some circuit boards in there, and off you go. What's the big deal?
Pulses,
what's the problem?
That's right.
Yeah.
That's right. It's got batteries, right? You plug it in. It can't be that complicated, right?
You just send your iPhone down hole. It has the same sensor.
Exactly.
So you said we have to remove cuttings. And so the guys also who do the air drilling, they also get that done, right? So we need something to remove the cuttings, but I guess mud or water or whatever is not the only thing that can remove cuttings. Any sort of circulating, fluid-like thing can remove the cuttings, right?
Correct.
Okay, cool. Well, then like David said, in the two basic types, kind of the layman understand is water-based mud versus oil-based mud. So why are those two things used? Or what are the different reasons for the different types of mud?
Yeah. Cost would be number one.
Yep. Water's cheaper.
Water's a lot cheaper than diesel.
Okay. Yep.
And then number two is going to be environmental.
Yep.
Environmental aspects. There's areas where you just can't, they won't allow you to drill with oil-based mud.
Well, so what's better about oil-based mud, the diesel-based mud, than the water-based mud? Where does it excel over where the water-based mud doesn't?
Lubricity.
Yep.
Lubricity's number one. Number two would be reactive formations. If you have shale that reacts to water, what happens is when water gets into shale, it swells. And it's it's called a pregnant shale, and that's when it'll fall in on you when you have too much water getting into the formation through your filter cake. Well, obviously, if your base fluid is oil versus water, there's a lot less chance of that happening, and it requires less modification from expensive chemicals.
And lubricity factor, is that just to literally lubricate the BHA going through the hole, or what else does that do for you?
But your filter cake you want your filter cake, which is the essentially the lining between the formation you're drilling and your drill string. The fluid creates what's called a filter cake. And with oil base, that filter cake is significantly slicker.
Okay.
And so it provides lubricity to the whole wellbore. Everywhere you've got metal touching that wellbore.
Yep.
Is significantly. And that makes it easy
to transfer weight, not get stuck, all this kind of stuff.
Exactly. Right? Reduced torque. The biggest deal is torque, obviously. It keeps your on bottom and off bottom torque significantly lower.
Yeah, one of the jokes we like to talk about in NVD is that we developed all these shock and vibe indicators, and they give you a green, yellow, red as far as good, bad, good, medium, and bad. And I think everybody got it backwards, because it's they look at it as red, high shock and vibe. I'm doing a good job, right? I'm really beating the crap out of it down there. And they almost treated red like green, because it took a long time for them to realize no, guys, you want it to be green because you want the energy to go into breaking up the rock and not breaking the tool. And if we're breaking the tool, we're not breaking the rock. And so
that's exactly right.
Well, that's good to think about as far as from a torque perspective as well with lubricity, right? And so, But the filter cake, I mean, I've heard that a lot, but this is just from my understanding, it's a layer of I guess little bit broken up pieces of rock and the fluid and additives of the fluid that are just kind of compounding in between the rotation. It's getting kind of packed off or packed into the outside of the hole, right? As you're rotating and pumping and everything else, right? It's kind of a naturally forming thing that, I mean, it sounds kind of convenient that it just naturally forms and it kind of helps you out, right?
Oh yeah. I mean, it essentially provides you a shell of protection between your brand new built formation and then where you're creating all of this friction that, you would think in your brain would potentially knock that formation back in on top of you if you thought about it with a shovel.
Mm-hmm.
One question I've always had is the mud system is closed loop, right? I mean, sort of. You're pumping in fluid and getting some of it back. What percentage of it do you lose, and like how much of the mud is reused on like the next job, or how does that work?
Well, it kind of like everything, it depends.
Right.
How much are you losing downhole? You know, some environments, you know, you're losing 200 barrels of stand downhole.
Wow.
So you're replacing a boatload of fluid, but ideally we only estimate, like from a solid control standpoint, on a bad solid control setup, for every foot you drill, you lose a foot of fluid between cuttings and wellbore.
Okay.
So if you're at, you know, 0.05 barrels per foot, for every foot you drill, you're losing 0.05 barrels per foot of fluid that you have to replace with either diesel or water or fresh built mud.
Mm-hmm.
And you're saying that's like a worst case number, or like a bad number?
A bad number is 1 to 1, 1.25 to 1 is kind of a bad number.
Okay. And 0.05 is like you got it dialed in.
Yep, that's exactly right. You'd really be recovering, just getting rid of your solids and recovering all of your, you know, good mud, getting rid of your low gravity solids and keeping your, you know, whether it's barite or if you're not using any high gravity solids.
Yep.
You know.
Another question. One other question I had was like, we talked about hydrostatic pressure, you know, pushing back against the formation as you're drilling. Can you get too heavy on the mud, or is it mostly just like you have to reach the minimum mud weight, and then if you're a little bit above that, that's okay, or is that problematic as well to be too high?
If it's too high, that's when you lose. We do what's called a formation integrity test, right? A fit test. And so we with the pumps, essentially we create pressure on the wellbore to an extent where our offsets have told us, okay, this, you know, let's say it's a 10-pound drilling fluid, and we, you know, we're going to pressure up our formation test might go to like 10.2. And so we feel good about, okay, we're not losing mud down hole at 10.2 hydrostatic, you know, so as long as we stay, you know, 10.1 heavy or lower, we're okay. But if you go to 10.3, you could lose all of it.
And why is that? So, because it just breaks the formation and starts.
That formation can only handle so much hydrostatic before it just loses its integrity and you fracture it.
Okay.
And that, so it is a pretty fine line then. It's not real forgiving.
It depends on where you are, but on the high end, it's typically, there's a pretty fine line. Sometimes it could be like I said, it could be 1 pound, you know, a tenth of a pound per gallon. You could never lose a drop. And if you go over that, if you go from 10.1 to 10.2, you could lose all of it.
All of it, but meaning you fracture the formation and everything you pump into is just gone.
Yep, you start pumping it away. You'll just start pumping it away. So if you're pumping it, you know, if you're pumping it 500 gallons a minute, you might be losing 20% of that or 30% of that downhole.
Ouch.
Wow.
Yeah, and if it's oil-based mud or a high dollar water-based polymer mud, you know, it's a big time deal to be losing it.
Yep. That's incredible. So what is one thing that you wish everyone knew about drilling mud? Everybody's involved in the drilling operation.
One thing I wish everybody knew was how much you lose on that solids control. From my side, it's kind of a whole separate business, the solids control side, but everybody just assumes, okay, 6% low gravs. It's, you know, it's not too hard to reach. We can maintain 6% low gravity solids, which are the bad ones that eat up y'all's tools from the outside. It's like, you know, it's a sand blaster essentially at 5 or 6 or 7 or 1,000 gallons a minute. And so our goal is we want to keep that mud as clean as possible so your tools function optimally.
Yep.
And you don't eat up all the pump parts and, you know, everything else that fluid is touching. And so I wish people more understood better the solid side of it and how much fluid, at least on oil-based mud, how much fluid you actually lose to that solids control between drying shakers and rig shakers and centrifuges. And it's an expensive cost that helps you a lot, but it eats up a lot of fluid, and a lot of people, especially operators in the office, do not understand, you know, how much that actually goes away when you really control your solids well.
Interesting. And as far as low gravity solids, you're just talking about how it's not super easy or straightforward to keep those out? Like, obviously they should be seeking to be minimized, but it is a challenge in and of itself, right? And that has to do with like the centrifuges and cleaning and everything else like that.
Shaker screens, quality shakers. Yeah, it's a big equation, a whole other big equation, just like an MWD, just like the mud. And, you know, the guys that do it right, once you get it right and you have a good setup on a rig, it flows. It's smooth as butter, but it's expensive to get there. You know, good rig shakers are costly. Mostly everybody runs Brant Cobras that are 15 years old, and they just don't do a very good job. And, you know, shaker screens are an expendable. You know, you use them up, they wear out every, depending on what size shaker screens and how hard you're pumping and how fast you're drilling, you're going through a $250 screen, you know, sometimes every 20 hours, and there's, you know, 4 of them on every shaker. And so, you know, those are expensive. And you just, I don't know, people slack on the solids end of it, and it costs you in the long run, because you guys know as well as anybody, run a tool.
Yep.
Yeah. Could you tell us a little bit about LCM? Is that part of the mud fluid or drilling engineering?
Oh, yeah.
Fluid engineering?
Yeah,
what is
absolutely.
the purpose of it?
Absolutely. The purpose is LCM stands for lost circulation material, right? So what happens is, when like we were talking about, if your hydrostatic gets too high, if your ECD, your equivalent circulating density, your mud weight gets too high, you can fracture the wellbore. When you do that, you present a lot of problems. You obviously lose your hydrostatic there, and so that's a well control issue. And so what we do is we pump down LCM downhole to try to fill that gap. You know, whether you have little small micro fractures just due to a unstable wellbore, you know, a formation area that just isn't very strong, or you have an area where there are major caverns or caves, you know, downhole that you run into, that LCM can provide. Essentially, it's like a sponge that fills that hole, and you just jam it in there, and you know, your fluid will flow wherever it can go the easiest, right? So if you can get those microfractures or major fractures plugged up with LCM, you don't reduce your wellbore is secure, and you're not losing all that money in mud that goes away and may never come back.
So if the formation
you got super fine, you know, LCM, you've got coarse, you've got medium, all the way up to cottonseed holes and, you know, super, super coarse, heavy cedar fiber type of LCM products.
Interesting. So I mean, there are some tools that you can pull out if it does fracture on you and you're losing fluid. You're not just done. You've got some backup.
Oh, absolutely
plans, right?
not. Absolutely not. You can, I mean, you know, up in the Texas Panhandle, Oklahoma Panhandle, we're drilling nonstop with 25 pounds per barrel cottonseed holes in the whole system all the time. And you just bypass the shakers and, you know, manage your cuttings. Yeah, it's probably would be a living nightmare for a tool company. But yeah, I mean, you're running, you have to maintain. If you don't maintain at least 20 pounds per barrel all the time, you can't keep enough fluid in the pits to drill.
No, that's incredible. Well, so how big is well control? Like, you know, I know a lot of well control techniques include weighting up mud or, you know, pumping large pills of, you know, super heavy dense mud, et cetera. How much of that is your day to day? I mean, are you guys planning for that every single well? Is that something you always have on standby? Is it something you do, you know, when you encounter that situation? Because it's pretty easy to bring it up in the moment. How does that work?
It depends on the area, what basin you're working in. If you're up in the mountains in Colorado or Wyoming where there's monster downhole losses, you probably do always have a frac tank or two of a big LCM pill to help you with well control as far as losses. But as far as like if you're drilling underbalanced and you're worried about stuff coming back at you, you know, we'll try to manage that with our regular weight system, whether it's an orbit valve where we can control that pressure down hole, or, you know, just our mud weight, maintain our hydrostatic at a certain level where we know we're holding back any sort of a water flow or a gas influx or anything like that. But when we go to tripping pipe or something and we reduce our hydrostatic by killing those pumps, we'll already have an idea of what we need to come up with mud weight wise and volume wise to pump and spot, where that TVD starts changing, where we can maintain a certain hydrostatic pressure where the well is under control.
Gotcha.
But it's kind of on the fly on that deal. It's a basic algebra, equation. You come up with it, and we pump what needs to be pumped.
Well, so going back to the basics a little bit, you said that there was a more than just the two types, right? So you have oil and water. I heard brine. What else is there?
You have a bunch of eco-friendly, like Invermol, almost like you'd think of a vegetable oil.
Okay.
Base fluid. They do that a lot in the ocean. It's like a synthetic more environmentally friendly oil-based mud.
Okay, so where they don't want to use water, they need something better than water, but they can't use diesel offshore, right? Because we can't just be bumping diesel into the ocean, right?
That's exactly right. It's called like an ester olefin would be what it's called, is the name of the fluid. But yeah, it's really vegetable oils, essentially layman's terms. But yeah, you can run something like that. You can run it's not quite oil-based, but we call it like brine diesel emulsion. It's a kind of a cheap oil-based mud where it's 50-50 with brine and diesel.
Okay.
And we run it out in the Permian a lot in the vertical sections, because if you're in an area where that vertical section is a little more reactive, you can run that and you have a little better control of your fluid as far as water going into the formation, but it's also not quite as expensive as using 100% diesel. And it helps eliminate washouts in areas like salt sections, because you've got a little higher salinity in it, so you're not eating out that salt formation with fresh water. But you've also got a little bit of diesel in there, so it helps you overall with lubricity and everything else without quite the cost of oil-based mud.
So what can you learn by the mud that's coming back as you're drilling? What do you analyze on that?
You can learn if you're taking some sort of a water influx downhole.
Okay.
Because that'll change your properties. That'll change whether, if you're drilling with oil-based mud, you've got a set oil-water ratio you're trying to run, whether it's an 80-20 or a 75-25 oil-water ratio. If you're taking a brine or a produce water kick, influx from downhole, that number will change on you compared from what you're sending downhole to what you're getting out of the hole.
Okay.
You can also tell with returns if you're having like a rubble zone, like a pregnant shale or something. If you're cutting, ideally in our laterals, if we're drilling an 8.5 inch hole or 7 7/8, your cuttings kind of look like coffee grounds coming back with oil-based mud. That's a perfect. That looks good. If they start coming back looking shardy, like broken glass, or long or thin or big rocks, chunky type of stuff, you're having a reactive or a hydrostatic issue down there that's going to cause you problems if you don't fix it real quick. Because that's the evidence that it's either falling in on you, or you're not controlling your water that's getting into the formation enough, and so it's getting that shell, what we call pregnant, where it falls in. So that the shell shakers will tell you that information.
Okay.
Interesting. Well, Dave, I got kind of a good wrap-up question, I think, unless you got any more.
No, let's do it.
Okay, so it sounds like a lot of this is like kind of proven down to like a science, right? Like where you can get the offset well data. It's pretty cool that you can actually buy, like, hey man, what worked for you? $50. I'm sure it's more than that, right? Just tell me. I'm sure it is. That's above my pay grade, but yeah, it's available. That's pretty cool. Maybe just horse trade for that info, right? But
right.
What part of the the mud engineering job is still much more of a dark art than a science at this point, right? Like where does it really vary on a case by case basis, and like where do you have to come in and apply all the science, all your knowledge to really solve a problem?
Here's scenario A, here's what we do. When it becomes more of a dark art, it's more about okay, we're losing mud downhole at, we know roughly where it's at. We've also got X amount of gas influx happening here. You could have 3 or 4 stories happening in a 3-mile well bore. It's it's the nightmare mud engineer scenario. You've got 2 or 3 things happening to you, and you have to affect the all three of them without ruining, potentially a, multi-million dollar wellbore for an operator.
At the NWD company, as the guys working on NWD tools, I mean, the worst I can do is get myself kicked off of a job, right? Like there's not really a way that I can make an NWD tool fail so badly that the entire well is lost. I guess we can drill the curve in the wrong direction. That's about the worst we can do, right?
I was about to say, go the opposite azimuth.
Yeah. Well, that shouldn't happen, but it does, right? But I can't destroy an entire lateral by doing a whoopsie, right?
That's right.
I guess.
If somebody's watching anyway.
Maybe I'm full of it. Maybe we can do just as much damage. I don't know. But it seems like you guys can do a little bit more damage than us. But it sounds like, even if you've done 10 offset wells or like you're on the 11th well of a, 12 well pad or something, you could like have seen a whole bunch of stuff from the other 10 wells. And then you could still be presented with like 2 or 3 unique scenarios on this one particular bore that requires all your experience in the science and math to solve that problem. And you got to solve it all by, controlling what you put in the mud, how much you pump, wind, pressures, all this kind of stuff. You got to take all that into account. Like this is not easy stuff.
That's exactly right. Well, it's like I tell anybody, whatever your specificity is, like for you guys, MWD tools, downhole tools, once your guys get in there and have, even a few years of experience, it's not rocket science anymore. It kind of becomes just what you do. Yep. But for somebody looking into it, it would be very overwhelming. Like my first, time on a job, for sure. I thought I was, swimming in 10-foot chop, 5 miles offshore. But once you kind of learn, it's really not as complicated as it sounds. Once you've spent 3 or 4 years doing it, and then it just kind of becomes second nature. But yeah, you definitely have to do some problem solving. Every wellbore is different. I don't care if you drill 20 on the same pad. They're all different. Some of them are really, really cookie cutter. And, 8 out of 10, you'll have no trouble. But, I mean, I'm on pads in the Permian where we'll drill one and have no H2S, no flow, no issues, and scoot over 30 feet and have a 100-gallon-per-hour wellbore influx with produce water.
Well, wow. Look, I'm all for technology and automation and machine learning and AI and all this kind of stuff. But like conversations like this just remind me like what a mind-bogglingly complicated interlinked problem drilling is, right? Yep. Like it's just so crazy. Like even like the amount of like what we call factory drilling today. Like, I mean, it's factory in that we're setting up to do the same thing every time, but it's not like a CNC machine where like you get it set up with the G code and it's going to cut the aluminum the same way. And like, you're not, I mean, it's like the equivalent analogy would be like you're feeding into the machine wildly varying, qualities of aluminum piece by piece by piece and like having to deal with each one individually. And like every well on a pad being different, like that's not factory. Like, that's like, we're doing it consistently. We're digging 10 holes in the ground, but they're all different. And like automating that or putting machine learning behind it is a much bigger challenge than I think a lot of people think. Not that they shouldn't be try it, but like it is a really complicated problem. It's just crazy.
That's exactly right. Yeah, there's a lot of companies trying right now to use AI to be their mud checker and keep a machine where it's running through their system all the time in a pit, and they can pull things like chlorides and PF, MF, and alkalinities, and they're having a really hard time doing it because things change all the time downhole. And so it's, it becomes quite a challenge where in the perfect world, we'd like to eliminate the human error element or the fact that a guy's got to actually be checking his mud to give you the numbers that you want. And, if you had AI, if you had a skid sitting out there that mud was going through all the time and could just pull those numbers on its own, it would know, okay, tell the derrick man to mix 15 sacks of caustic or, tell them to mix this product or that product, but things change so often, wellbore to wellbore, especially basin to basin, that's really hard to do.
I guess I'll just wrap with this, but like, I'm kind of like a proponent and critical of AI and ML and everything else like that at the same time. But like, to me, I never look at it as like, I want to eliminate human error or I want to eliminate, the human factor. I mean, humans make mistakes as well. Computers make mistakes as well. It happens, right? But like the way I see it is I want AI and ML to automate everything that's like just simple and easy to explain and consistent so that the humans that are involved can spend all of their power on the creative thinking, right? And not doing any of the, consistent, redundant day-to-day stuff. Because human minds are still so far ahead of AI that it's just insane. And I think we should be focusing on maximizing that and not eliminating people. But anyways, you're going to get me on like a totally separate podcast if I keep going there. But Michael, this is fantastic. I learned a lot. Thank you very much. Is there anything else you'd like us to add or know as we wrap up?
Oh, no, sir. Thank you so much for having me.
That's all the time we have for today. Thank you again, Michael, for joining us. I sure learned a lot. Be sure to check out our podcast on iTunes, Spotify, and YouTube, and leave a review and subscribe. Thank you for tuning in.